The cosmos is not just growing, it is speeding up. For nearly a century we have known the universe expands, but the true nature of this acceleration remains our greatest scientific enigma. By the end of this journey, you will understand the 25 deepest questions keeping cosmologists awake at night. We will confront a force that makes up most of reality yet is completely invisible, and grapple with a measurement so baffling it threatens to rewrite physics itself. This is a fun and mind-bending exploration of the ultimate unknown. What single cosmic mystery do you find most unsettling? The very first question is the most profound. What exactly is dark energy? This is not just a puzzle, it is the central enigma of modern cosmology. The term itself is a placeholder for our ignorance, a name given to whatever is causing the expansion of the universe to speed up. For decades, astronomers assumed the gravitational pull of all matter would be slowing the cosmic expansion down. Then, in the late 1990s, two independent teams made a shocking discovery. By observing incredibly distant stellar explosions called Type I supernova, which act as standard candles for measuring cosmic distances, they found the universe was not slowing at all. The most distant galaxies were receding faster than expected. The expansion was accelerating. Something was actively pushing space itself apart. That something is what we call dark energy. Its properties are as bizarre as they are fundamental. Dark energy appears to have a kind of negative pressure. Think of the fabric of space not as a passive stage, but as an active participant with an inherent energy. This energy exerts a repulsive force, a sort of anti-gravity that works against the attractive pull of all the matter in the cosmos. It is not concentrated in galaxies or stars, but is smoothly and evenly distributed, permeating every single cubic centimeter of the vacuum of space. And its dominance is staggering. Current measurements suggest dark energy makes up roughly 68% of the total energy content of the entire universe. The stars, planets, galaxies, and all the dust and gas we see and love constitute less than 5%. The rest is dark matter, so the force we understand the least is the one that controls the ultimate fate of everything. Yet for all we know about its effects, its true nature remains utterly unknown. The simplest explanation, proposed by Einstein himself long before the acceleration was discovered, is the cosmological constant. This idea treats dark energy as a fixed, immutable property of empty space itself, a constant energy density that never changes. But this leads to profound theoretical headaches, like the infamous vacuum catastrophe where predicted and observed energy densities disagree by a factor of 1 followed by 120 zeros. Other theories suggest dark energy is not constant at all, but a dynamic field that changes over time, sometimes called quintessence. Or perhaps it is not a new form of energy at all, but a sign that our theory of gravity, Einstein's magnificent general relativity, breaks down on the largest cosmic scales. We have given the driver of the cosmos a name, but we are still completely in the dark about who or what is actually behind the wheel. This leads us directly to the second great puzzle, one that questions the very stability of reality. Is the cosmological constant really constant? Einstein originally introduced this term, represented by the Greek letter lambda, as a fudge factor to keep his equations describing a static, unchanging universe. He later called it his greatest blunder when the expansion of the universe was discovered, but the idea was resurrected in a stunning twist. If dark energy is Einstein's cosmological constant, then it is exactly that, a constant. It means the repulsive force woven into the fabric of empty space has always been the same strength, from the first moments after the Big Bang to the distant future, and it will never change. This is the simplest explanation, and so far, our most precise observations have not ruled it out. But simplicity in cosmology is often a mirage. What if the driver of cosmic acceleration is not a fixed feature of the universe but something that changes? This is the heart of theories like quintessence, named after the ancient fifth element. In this idea, dark energy is not a constant property of space but a dynamic field that permeates it, much like the Higgs field that gives particles mass but with a crucial difference. A quintessence field could slowly evolve over billions of years, its strength waxing or waning. This would mean the repulsive force pushing galaxies apart was different in the past and will be different in the future. The implications are staggering. If dark energy strengthens over time, it could lead to a truly apocalyptic end for the cosmos, a big rip where even atoms are torn apart. If it weakens, gravity might one day regain control. So how do we test this? Astronomers are becoming cosmic historians, using the universe itself as a time machine. They are meticulously measuring the expansion rate across different epochs of cosmic history. By looking at extremely distant supernova, the ancient light from quasars, and the large-scale structure of galaxies imprinted in the cosmic microwave background, they are trying to construct a movie of the universe's expansion, not just a snapshot. They are searching for any subtle deviation, any hint that the acceleration rate was slightly slower or faster billions of years ago compared to now. Finding such a change would be a monumental discovery. It would mean that dark energy is dynamic, that the cosmological constant is not constant at all. This would not just adjust our models, it would force a revolution in fundamental physics, revealing a new, evolving component of reality that we have only just begun to suspect. The search for this tiny signal, buried in the light of ancient stars, is one of the most delicate hunts in all of science. Our fate hinges entirely on the answer to that last question. If dark energy is truly a constant cosmological force, the future of the cosmos is a long, cold, and lonely one. This is the scenario often called the Big Freeze, or more formally, heat death. Picture the universe's expansion continuing to accelerate steadily, relentlessly. Distant galaxies we see today will one day be pushed so far away that their light can no longer reach us. The observable universe will shrink to include only our own local group of gravitationally bound galaxies. Over trillions upon trillions of years, star formation will cease as all interstellar gas is used up or flung beyond reach. Existing stars will burn out one by one, leaving behind cold remnants, black holes, and drifting planets. Even these will not last forever. Current theories suggest that over timescales so vast they defy comprehension, even black holes will slowly evaporate through a process called Hawking radiation. The universe would become an unimaginably vast, ever-expanding void, filled with a thin, cold sea of diluted particles and radiation, with no energy gradients left to do any work, no heat, and no possibility for change. It is the ultimate equilibrium, a permanent and silent end, but that is only if dark energy remains constant. If it is a dynamic force like quintessence that grows stronger over time, the ending becomes far more violent and dramatic, a cosmic finale known as the Big Rip. In this scenario, the repulsive force of dark energy doesn't just push galaxies apart, it eventually overcomes every force that holds things together. First, the acceleration would shred the cosmic web, tearing galaxy clusters apart. Then, it would rip individual galaxies from themselves. Later, as the force grows unimaginably strong within our own galaxy, it would pull stars away from each other. In the final moments, just before a theoretical end time, the force would exceed the gravitational and electromagnetic bonds holding our solar system, our planet, and even our own bodies together. Earth would be pulled from the sun. Then, the very atoms that make up everything would be torn apart as the repulsive force between particles overwhelms the nuclear forces binding them. The universe would end not with a whimper, but with a catastrophic, fundamental shredding of spacetime itself. There is a third, more nostalgic possibility, though it seems increasingly unlikely given our observations. This is the big crunch, a reversal of the expansion. If dark energy were to weaken significantly, or if there were far more matter in the universe than we think, gravity could eventually win the cosmic tug of war. The expansion would slow, halt, and then reverse. Galaxies would begin rushing back toward each other, the universe heating up as it collapses. All matter and energy would be compressed back into an ultra-hot, ultra-dense state, perhaps even triggering a new Big Bang, leading to a cyclic or oscillating universe with no true beginning or end. While this idea has a certain poetic symmetry, our measurements of accelerating expansion make it a distant contender. Yet it reminds us that the ultimate fate is not written. It is a direct consequence of a contest between two invisible titans, the relentless push of dark energy and the enduring pull of gravity, and we still do not know which one will have the final word. The destiny of every galaxy, every star, every atom rests on the answer to a question we have only just begun to ask. The ultimate fate of the cosmos is a question of speed. How fast is the universe expanding right now? This seemingly simple measurement, known as the Hubble constant, has ignited a full-blown crisis in cosmology, a puzzle so persistent it is called the Hubble Tension. At its heart is a baffling discrepancy between two of our most trusted methods for taking the universe's pulse. The first method looks back to the infant universe, to the cosmic microwave background, that faint afterglow of the Big Bang. By meticulously mapping the tiny temperature fluctuations in this ancient light, scientists can calculate the ingredients of the early cosmos, how much dark matter, normal matter, and dark energy it contained. They then feed these numbers into our standard model of cosmology and run the cosmic film forward, predicting what the expansion rate should be today. This is a pristine, early universe measurement. The second method is a local check-up. Astronomers build a cosmic distance ladder within our own galactic neighborhood. They start with geometric techniques like parallax to measure distances to nearby stars. They then use those stars to calibrate pulsating stars called Cepheid variables, whose intrinsic brightness is linked to their pulse rate. Seeing how bright a Cepheid appears tells us its distance. These Cepheids are then used to calibrate even brighter cosmic beacons, Type 1, a supernova, in nearby galaxies. By observing how fast those galaxies are moving away from us and knowing their precise distances from the ladder, we can measure the expansion rate directly in the present-day universe. Both methods are exquisitely precise, the result of decades of painstaking work, yet they stubbornly disagree. The early universe method, using the cosmic microwave background, predicts a slower expansion rate. The local distance ladder method, using Cepheids and supernova, measures a faster one. The gap is not large, only about 10%, but it is far greater than the estimated margins of error for either technique. This is not a minor glitch, it is a persistent, glaring inconsistency. Either there is a hidden systematic error in one of our most delicate measurements, something we have overlooked in the flicker of ancient light or the pulse of distant stars, or this tension is a crack in the foundation. It could be the first real evidence that our standard model of cosmology, the lambda-cold dark matter model, is incomplete. Perhaps dark energy is not constant but evolving in a way we did not anticipate. Maybe there is an unknown type of neutrino or a strange interaction in the dark sector. The Hubble tension is more than a number, it is a beacon pointing toward physics we have yet to discover. This stubborn discrepancy in the universe's expansion rate is not a dead end, it is an open door. Could new physics resolve the Hubble tension? Cosmologists are treating this puzzle not as a failure, but as a golden opportunity, a clue that our cosmic model needs an upgrade. The most promising ideas involve tweaking the ingredients of the early universe in ways that would leave the cosmic microwave background looking largely the same but predict a faster expansion today. One fascinating proposal is early dark energy. Imagine that just after the Big Bang, for a brief cosmic instant, there was an extra burst of this repulsive force. This temporary surge would have subtly altered how sound waves traveled through the primordial plasma, changing the detailed blueprint imprinted on the cosmic microwave background. If scientists recalculate the early universe with this brief extra push included, the predicted expansion rate for today can jump up, potentially aligning with the faster local measurements. It is as if the infant universe had a growth spurt we did not account for, and we are seeing the consequences billions of years later. But early dark energy is just one character in a cast of theoretical suspects. Perhaps the solution lies with ghostly particles we already know exist, neutrinos. What if some neutrinos have unusual properties, like being significantly heavier than we think? Or if there exists a completely new, sterile type of neutrino that interacts only through gravity? These particles would have flown through the early cosmos, influencing how structures formed and again, shifting the predicted present-day expansion rate. Another profound possibility is that the two dark titans are not independent. What if dark matter and dark energy interact with each other in some hidden way? In our standard model, they are separate entities, one clumping to form cosmic scaffolding, the other smoothly pushing space apart. But if they exchanged energy in the universe's youth, it would change the timeline of cosmic evolution, potentially easing the tension between our two measurements. Even our understanding of dark matter itself is being questioned. The model assumes it is cold, meaning its particles moved slowly in the early universe, which is why it clumped so efficiently to form galaxies. But what if dark matter is slightly warm, moving just a bit faster? Or what if dark matter particles can interact with themselves, bouncing off each other? These subtle changes would affect how quickly galaxies and clusters assembled, again tweaking the cosmic calculations that lead to today's predicted expansion rate. Each of these ideas is a potential key to the lock. The Hubble tension is more than a problem to be solved. It is a beacon shining on the frontier of our knowledge, hinting that the universe holds secrets even more strange and wonderful than we have yet dared to imagine. But this hunt for new physics rests on a foundational assumption, one so deeply embedded in cosmology we rarely even question it. This brings us to our sixth great mystery: is the universe's expansion truly uniform? For over a century, the guiding rule has been the cosmological principle. It states that on the largest scales, the universe is both isotropic and homogeneous. Isotropic means it looks the same in every direction, no special axis or preferred center. Homogeneous means matter is evenly distributed when you zoom out far enough. It is the idea that our place in the cosmos is utterly ordinary, not special in any way. This principle is the bedrock upon which we built our models from the Big Bang to dark energy. But what if, on the grandest scales we can observe, this principle begins to crack? Astronomers are now finding tantalizing hints that the universe's expansion might not be perfectly even. Some studies of distant supernova and galaxy clusters suggest a strange cosmic lopsidedness, a so-called dipole. The data hints that expansion appears to be slightly faster in one direction of the sky and slower in the opposite direction, as if we are caught in a subtle cosmic current. One provocative explanation is the idea of a Hubble bubble. Imagine our local region of space, out to perhaps a few 100 million light-years, is inside an underdense cosmic void, a vast bubble where matter is slightly more sparse than the cosmic average. Inside this bubble, the gravitational tug from surrounding matter is weaker, so the repulsive push of dark energy has less to fight against. This could make the expansion rate measured locally inside our bubble appear faster than the true global average. It would be a colossal local illusion, a trick of our cosmic address that might explain the Hubble tension without any new physics at all. Then there are the structures themselves, titans that strain the very definition of homogeneity. We have mapped cosmic features like the Sloan Great Wall, a filament of galaxies over 1.4 billion light-years long, and the Boötes void, a spherical region of near emptiness hundreds of millions of light-years across. These are not mere galaxies, they are continents in the cosmic ocean. Could such immense structures, with their vastly different densities of matter, create local variations in the expansion rate? Gravity from a supercluster might slightly break expansion in its vicinity, while the emptiness of a void might allow space to stretch faster. If these effects are real, then the Hubble constant we measure might not be a single universal number, but more like a local weather report, different depending on which cosmic neighborhood you are in. The cosmological principle is being stress-tested as never before. If it fails, the implications are profound. It would mean the universe has a preferred direction or a large-scale texture we never anticipated, forcing us to redraw the cosmic map from its very foundations. The uniformity of the cosmos, or the lack of it, points us back to the universe's very first moments. To understand the expansion we see today, we must confront the most explosive growth spurt of all, cosmic inflation. This is not the slow, dark energy-driven acceleration we observe now, but a different beast entirely. In the first fraction of a second after the Big Bang, a minuscule patch of space is thought to have undergone an exponential, faster-than-light expansion, inflating from a subatomic speck to a volume larger than our observable universe in an instant. This theory solves several profound puzzles, like why the universe is so flat and uniform on large scales. It smoothed out any initial wrinkles and set the stage for everything to come. The engine behind this primordial blast was likely a hypothetical scalar field, often called the inflaton field, which temporarily imbued space with a tremendous repulsive energy. Then, as abruptly as it began, inflation ended. The inflaton field decayed, dumping its energy into the hot, dense soup of particles that would become the matter and radiation of the classic Big Bang. But here lies a deep and unsolved mystery. What is the connection, if any, between that inflaton field of the distant past and the dark energy field permeating space today? Both seem to be properties of empty space itself that cause repulsive gravity. Are they two faces of the same fundamental force, manifesting at different times with vastly different strengths? Or are they completely unrelated phenomena, one a brief, violent event and the other a slow, steady pressure? The answer could lie in understanding what made inflation stop. The process is often compared to a ball rolling down a hill in a landscape of energy. At the top, the ball's position represents the high energy state that drives rapid expansion. As it rolls down into a valley, inflation ends and the energy is converted. But what if the ball did not settle at the very bottom? What if it came to rest on a shallow plateau, a region of low but non-zero energy? That leftover, latent energy of the vacuum could be what we now measure as the cosmological constant, our dark energy. In this view, the universe's initial burst and its current acceleration are chapters in the same story, driven by the same underlying field that simply shifted to a lower gear. Unraveling this connection is more than cosmic archaeology. It is a direct probe into the true nature of the vacuum. The empty space around us is not nothing, it seethes with quantum activity. The energy of this quantum vacuum is a prime candidate for dark energy, but its predicted strength is catastrophically wrong. If we can understand how inflation connected to the vacuum we have now, we might finally solve that infamous vacuum catastrophe and learn why empty space weighs what it does. The first split second of creation might hold the key to the fate of the entire future. The quest to measure dark energy is a story of cosmic cartography, a desperate attempt to map an expanding universe with no fixed landmarks. This brings us to the eighth great mystery. How do we accurately measure cosmic distances? The answer is not a single tool, but a fragile, ingenious construction called the cosmic distance ladder. Each rung of this ladder relies on the one below it, and a tiny error at the bottom can cascade into a crisis at the top, which is precisely what may be fueling the Hubble tension. The first rung is the most direct, a technique called parallax. Hold your thumb out at arm's length and close one eye, then switch eyes. Your thumb appears to jump against the background. Astronomers do the same thing with stars, using Earth's orbit around the Sun as a giant baseline. By measuring the tiny apparent shift of a nearby star against more distant ones over 6 months, we can calculate its distance through simple trigonometry. This method is rock solid, but it only works for stars within a few thousand light years, a mere stone's throw in cosmic terms. To reach further, we need a brighter beacon whose true brightness we can deduce. This is where Cepheid variable stars become crucial. These are pulsating stars whose intrinsic luminosity is linked to their pulsation period. A Cepheid that takes 10 days to brighten and dim is always about 7,000 times more luminous than our Sun. By measuring its pulsation period from Earth, we know its true power. Then, by seeing how faint it appears to us, we can calculate its distance. Cepheids are the first true standard candles, and they let us measure distances to nearby galaxies. But here lies a critical uncertainty. The entire Cepheid scale must be anchored by parallax measurements of a few of these stars in our own galaxy. If those anchored distances are off by even a small amount, every rung above them is skewed. This brings us to the James Webb Space Telescope and its revolutionary role. Webb's sharp infrared eyes are now measuring Cepheids in the galaxy that hosts our most important local supernova with unprecedented precision. It is peering through the dust that obscured previous measurements, aiming to nail down the true brightness of these crucial stars. The hope is that Webb will either solidify the local distance ladder or reveal a hidden calibration error, potentially resolving the Hubble tension by fixing the first rung. With Cepheids calibrated, we climb to the next rung, the universe's ultimate mile markers, Type 1, a supernova. These are thermonuclear explosions of white dwarf stars that reach a very specific, predictable peak brightness. Because they are so incredibly luminous, they can be seen in galaxies billions of light years away. By comparing how bright a distant Type 1, a supernova, appears to its known true brightness, we can calculate the distance to its host galaxy. This is the method that revealed the accelerating expansion, but even these standard candles are not perfect. Astronomers must carefully correct for how interstellar dust dims their light and account for subtle variations in the explosions themselves. The final, overarching measurement comes from redshift. As the universe expands, it stretches the light waves traveling through it, shifting them toward the red end of the spectrum, like the fading siren of a receding ambulance. By measuring how much a galaxy's light has been redshifted, we know how fast it is receding from us. Combine that velocity with an independent distance measurement from the supernova, and you get the expansion rate, the Hubble constant. The terrifying beauty of this entire ladder is its interconnected fragility. A millimeter of error in the parallax rung becomes a kilometer of error at the supernova rung, billions of light years away. The entire monumental effort to weigh dark energy and divine the fate of the cosmos rests on our ability to correctly measure the flicker of a few pulsating stars in our own galactic backyard. The cosmic distance ladder reveals more than just speed. It hints at the very architecture of reality. This brings us to the ninth profound question: what is the shape of the universe? We often picture space as an endless, featureless void, but its overall geometry is a direct consequence of the cosmic tug of war between expansion and gravity, dictated by the total density of all the energy and matter it contains. There are three classical possibilities, each a different answer to a simple, ancient question: does parallel lines ever meet? The first possibility is a flat universe. This is the geometry we learn in school, where parallel lines remain parallel forever. The angles of a triangle add up to 180 degrees, and space has no intrinsic curvature. A flat geometry implies the universe's density is exactly at a critical value, perfectly balanced between expansion and gravitational collapse. The second possibility is an open universe, often visualized as a saddle shape. Here, space curves outward in every direction. In this geometry, parallel lines would eventually diverge, and the angles of a triangle would sum to less than 180 degrees. An open universe would have a density below the critical value, meaning there is not enough matter and energy to ever halt the expansion, which would continue forever. The third possibility is a closed universe shaped like the three-dimensional surface of a giant sphere. In this geometry, parallel lines would eventually converge and cross like lines of longitude on a globe, and a triangle's angles would add up to more than 180 degrees. A closed universe has a density above the critical value, containing enough matter and energy that gravity would ultimately win, potentially leading to a big crunch. So, which one is our universe? Our most powerful evidence comes from that ancient snapshot, the cosmic microwave background. Scientists have analyzed the size of the temperature fluctuations, the hot and cold spots in exquisite detail. In a curved universe, whether open or closed, the fabric of space itself would act like a lens, magnifying or shrinking the apparent size of these patterns. After decades of measurement, from balloons to satellites like Planck, the answer is stunningly precise. The universe appears to be flat, or so nearly flat that we cannot detect any curvature. The data suggests the total density of the cosmos is within a razor-thin margin, about 0.5% of the critical value needed for flatness. This near-perfect flatness is actually a major piece of evidence for cosmic inflation, which would have stretched any initial curvature smooth. But that word, nearly, is crucial. Could the universe have a subtle, global curvature too faint for our current instruments to see? This is not just a technicality. If the universe is perfectly flat, it suggests a mysterious fine-tuning at the moment of the Big Bang, a density set to exactly the right value. A tiny deviation from flatness, however, would be a seismic discovery. It would force us to revise our understanding of inflation, dark energy, and dark matter. For instance, a slightly closed universe might imply the existence of additional, unknown forms of matter or energy pushing the density higher. It could also alter the ultimate fate, nudging the cosmos away from a perpetual dark energy-driven expansion toward a different destiny. The quest to measure the universe's shape with even greater precision is a direct probe into its deepest contents and its final chapter, a search for a bend in the fabric of everything that might rewrite the story written in the first light. The universe's flatness suggests a perfectly tuned geometry, but what if the true shape of reality is one we cannot see? This leads us to the 10th and perhaps most mind-bending question of all. Are there extra dimensions influencing the expansion? We are about to venture far beyond the familiar 3 dimensions of space and one of time into the speculative realms of string theory and brainworld cosmologies. These are not just abstract mathematical exercises, they are serious attempts to unify all the forces of nature, and in doing so, they may rewrite the story of cosmic acceleration. String theory, at its heart, proposes that the fundamental particles of the universe are not point-like dots, but unimaginably tiny, vibrating loops of energy or strings. For the mathematics of these vibrations to work consistently, they require more room to resonate than our everyday 4 dimensions provide. The theory suggests there could be 6 or 7 additional spatial dimensions, but they are curled up or compactified on a scale trillions of times smaller than an atom. Think of a garden hose. From a great distance, it looks like a simple one-dimensional line, but up close, you see it has a circular 2-dimensional surface. In the same way, every point in our familiar 3-dimensional space could hide a tiny, coiled-up multidimensional shape. Now enter brainworld cosmology, a dramatic extension of this idea. In this picture, our entire 3-dimensional universe might be a membrane, or brain for short, floating within a higher dimensional space called the bulk. All the matter and forces we know, like electromagnetism and the nuclear forces, could be stuck to our brain like paint on a canvas, But gravity, the architect of the cosmos, might be different. It could be the only force that can leak off our brain and propagate through the full bulk of higher dimensions. This leakage could have profound consequences for cosmology. On the tiny scales of particle physics, gravity is already mysteriously weak, billions of times weaker than the other forces. If it is diluted by spreading into extra dimensions, that could explain its feebleness. But on the vast scales of the expanding universe, this leakage could manifest as an apparent extra repulsive force. As gravity bleeds off our brain, its grip on the large-scale structure of the cosmos would weaken over cosmic distances. From our perspective, trapped on the brain, it would look exactly like a new form of anti-gravity, an accelerating expansion we mistakenly label as dark energy. In this radical view, dark energy is not a mysterious substance filling space, but a shadow, a geometric artifact of our universe's existence within a larger, hidden reality. It is the cosmic equivalent of seeing a two-dimensional shadow of a three-dimensional object and trying to understand the object's true shape. Some models even suggest that the collision of two brains in the bulk could have triggered our own Big Bang. While these ideas are currently untested and highly speculative, they represent a thrilling frontier. They challenge us to consider that the driver of the universe's fate may not be a what but a where, a consequence of the hidden architecture of reality itself. Hidden dimensions challenge our most basic assumptions about reality, but they force us to ask an even deeper question about the very stage on which the cosmic drama unfolds. What is the true nature of space-time itself? For centuries, we have treated space and time as a passive, continuous backdrop, an empty arena where matter and energy perform. But Einstein's revolution taught us that space-time is not just a stage, it is a dynamic, malleable participant, warping and curving in response to mass and energy. The expansion of the universe is the ultimate expression of this dynamism, space itself stretching over cosmic distances. Yet this raises a profound and almost philosophical puzzle. If space is expanding, what exactly is it that is growing? Is space-time a fundamental, irreducible fabric of reality, or could it be an emergent property, something that arises from a more basic, underlying structure, like temperature emerging from the frantic motion of molecules? This is not mere speculation, it is the cutting edge of quantum gravity, where our two most successful theories, general relativity and quantum mechanics, meet in violent contradiction. General relativity describes space-time as smooth and continuous, while quantum mechanics insists that at the tiniest scales, everything is granular and discrete. To reconcile them, physicists propose that space-time itself may have a fundamental graininess. One leading idea, loop quantum gravity, suggests space is not infinitely divisible. Instead, it is woven from a network of incredibly tiny, discrete loops, a fabric of finite threads. The smallest possible unit of space is thought to be the Planck length, about 1.6 times 10 to the negative 35 meters. That is so inconceivably small that if you enlarged an atom to the size of the observable universe, a Planck length would be roughly the height of a tree. At this scale, the smooth continuum of space-time dissolves into a seething, chaotic froth often called quantum foam. In this turbulent sea, tiny wormholes might blink in and out of existence, and the very concepts of before and after could break down. Now connect this to cosmic expansion. If space is an emergent property of this quantum network, then the expansion we measure might not be like stretching a rubber sheet, but more like the network itself generating new links, creating new volume from the underlying quantum code. Furthermore, this quantum foam is not empty. It teems with virtual particles that fleetingly pop into and out of existence, contributing to the vacuum energy. This is the infamous cosmological constant problem, where the predicted energy of this quantum vacuum is astronomically larger than the tiny value we observe for dark energy. Could the answer lie in the granularity of space itself? Perhaps the discrete structure of space-time at the Planck scale somehow cancels out or suppresses the wild quantum fluctuations, leaving only the faint residual energy we see as dark energy. Or perhaps the expansion of the universe is subtly altered by this microscopic graininess, like a pixelated image stretching in a way that a smooth one would not. While these scales are far beyond any direct experiment, the cosmic expansion we see across billions of light years might be the magnified echo of physics occurring at the very smallest possible scale, a whisper from the quantum foundation of reality telling us that space itself is born from something deeper. The quantum foam beneath space-time hints at a universe built from relationships, and nowhere is this more crucial than between its two dominant shadows. While dark matter sculpts the cosmos through gravity, does it also whisper to the engine of expansion? The Standard Model treats dark matter and dark energy as independent actors, one clumping to form the invisible skeleton of galaxies, the other smoothly stretching the space between them. But what if these two unknown giants are not strangers? What if they interact? This idea transforms our cosmic story from a solo performance into a complex duet. In interacting dark energy models, the two components can exchange energy, a hidden conversation happening across the vastness of space. Imagine dark matter slowly decaying into dark energy, feeding the repulsive force over billions of years. Or picture dark energy transferring its energy into dark matter, causing clumps of the invisible stuff to grow or dissipate in unexpected ways. This is not just a theoretical tweak, it has dramatic consequences for the narrative of our universe. The growth of cosmic structure, the assembly of galaxies and clusters from tiny seeds in the early universe, is exquisitely sensitive to the balance between gravity and expansion. If dark matter and dark energy are talking, that balance changes over time. For instance, if dark energy drains strength from dark matter, gravity's pull would weaken earlier in cosmic history. This would put the brakes on the formation of the largest galaxy clusters. The cosmic web we see today, with its vast filaments and dense nodes, would look different, sparser in some places, more concentrated in others. Conversely, if the interaction boosts dark matter's clumping power, we might expect to see more enormous galaxy clusters at certain epochs than our standard, non-interacting model predicts. This gives astronomers a powerful observational test. They are now creating the most detailed three-dimensional maps of the universe ever made, projects like the Dark Energy Spectroscopic Instrument, or DESI. By plotting the positions and distances of tens of millions of galaxies, they can measure the statistical distribution of matter, the so-called large-scale structure. They are looking for a specific signature, a subtle deviation in how clusters of galaxies are packed together across different distances, which correspond to different look-back times. Finding such a fingerprint in the cosmic web would be direct evidence of a hidden dialogue between the universe's two greatest mysteries. It would mean the dark sector is not a collection of isolated phenomena, but a complex, interconnected ecosystem. The fate of expansion would then depend not just on dark energy's strength, but on an ongoing, invisible negotiation that has been shaping everything from the largest voids to the destiny of every galaxy. This hidden conversation between dark matter and dark energy hinges on a single, crucial number, a value that could decide the fate of everything. This brings us to the 13th great mystery: what is the true value of the equation of state? In the language of cosmology, this is the most important number you have never heard of, represented by the letter W. It is the key that unlocks the nature of dark energy. The equation of state is simply the ratio of the pressure dark energy exerts to its energy density. Think of it as the personality profile of this cosmic force. For Einstein's cosmological constant, that personality is fixed and simple. Its pressure is negative and exactly equal to its energy density, giving it a value of W equals -1. This specific number produces the steady, relentless acceleration we have discussed. But what if W is not exactly -1? Even a tiny deviation, say -0.99 or -1.01, would be a scientific earthquake. It would mean dark energy is not a constant property of space, but something dynamic, a field-like quintessence that can change over time. A value greater than -1, say -0.95, would suggest a slightly weaker repulsion. A value less than -1, say -1.05, would indicate a phantom dark energy, a force so strange it could grow stronger as the universe expands, potentially leading to that catastrophic Big Rip. Measuring this number with exquisite precision is the holy grail of modern observational cosmology. It is not enough to know dark energy exists, we must know its character. This is the primary mission of a new generation of cosmic cartographers, telescopes and surveys designed to map the history of expansion with unprecedented detail. The Dark Energy Spectroscopic Instrument, or DESI, is currently measuring the spectra of tens of millions of galaxies, building a three-dimensional map of the universe stretching back 11 billion years. By studying the subtle patterns in this map, the Baryon acoustic oscillations, which are frozen sound waves from the early universe, scientists can measure how the expansion rate changed over cosmic epochs, directly probing the value of W. Soon, the European Space Agency's Euclid telescope will join the hunt from orbit, imaging billions of galaxies to trace the subtle warping of their light by dark matter, another way to weigh the influence of dark energy across time. And later this decade, NASA's Nancy Grace Roman Space Telescope will conduct its own vast survey, discovering thousands of distant supernovae to measure cosmic distances with phenomenal accuracy. Together, these missions are not just taking a snapshot, they are creating a high-definition movie of the universe's expansion. They are searching for any slight bend in the curve, any hint that the acceleration was a bit weaker or stronger in the distant past compared to today. Finding such a bend would mean W is not -1. It would be the definitive proof that dark energy evolves, that the cosmological constant is dead, and that we are witnessing a dynamic, changing component of reality in real time. The fate of the cosmos may be written in the value of a single, elusive number, and we are now building the machines to read it. Our quest to measure the equation of state pushes us to the very edge of time, to the moment of creation itself. But what if the Big Bang was not a true beginning? The expansion we see today might be just one chapter in an endless cosmic saga. This leads to the 14th profound question: was there a pre-Big Bang universe? The standard Big Bang model describes a singular origin, a moment of infinite density and temperature from which space, time, and all matter erupted. Yet that singularity is also a sign that our physics breaks down. It is a boundary, a wall beyond which our equations cannot see. Some cosmologists propose we should not think of it as a beginning, but as a transition, a dramatic turning point in an eternal cycle. In cyclic or bouncing universe models, our cosmos has no ultimate start or end. Instead, it undergoes endless epochs of expansion and contraction. Picture the universe we inhabit today, accelerating outward under the influence of dark energy. In a cyclic model, this expansion continues for an almost unimaginably long time, until dark energy eventually decays or transforms. Then, the relentless pull of gravity takes over. All matter and energy, now spread incredibly thin, begins to fall back together. The universe contracts, heating up as it collapses, heading toward what looks like a big crunch. But instead of crushing into a meaningless singularity, new physics from quantum gravity or string theory could come into play. At an incredibly high but finite density, a repulsive force, perhaps related to those same ideas that drove cosmic inflation, could bounce the contraction back into a new expansion. The Big Bang, in this view, was really a big bounce, a rebirth from the ashes of a previous cosmic phase. The universe would then expand again, cool, form galaxies and stars, and eventually be dominated by dark energy once more, setting the stage for the next cycle. It is a grand cosmic heartbeat pulsing across eternity. In other speculative models, like those emerging from string theory, our three-dimensional universe is a brain that periodically collides with a parallel brain in a higher dimensional bulk. Each collision transfers enormous energy, appearing within our brain as a hot, dense state we call the Big Bang. The universes then drift apart, expand and cool, only to be drawn together again for another collision billions of years later. So, could we ever find evidence for a universe before our own? The clues would be incredibly subtle, etched into the fabric of reality during the bounce or collision. One potential fingerprint could be hidden in the cosmic microwave background. If the previous cycle imprinted a pattern of gravitational waves or left a specific signature in the distribution of the hot and cold spots, it might still be faintly visible, a ghostly pattern from a time before time. Another hope lies with primordial gravitational waves, ripples in space-time from the universe's earliest violent moments. Future observatories might detect a background hum of these waves, and their specific spectrum could reveal whether they were generated in a singular inflationary event or in the chaotic dynamics of a bounce. Finding such evidence would be the ultimate cosmological revolution. It would mean our universe is not a one-time event but part of an infinite, timeless sequence. The expansion we tirelessly measure would then be just the current phase of a grand, eternal rhythm, a single breath in the life of a cosmos that has no beginning and no end. The shift from deceleration to acceleration marks a turning point in cosmic history. Roughly 5 billion years ago, the universe's expansion crossed a threshold, its gradual slowing reversed by the growing influence of dark energy. But why did this happen at that specific moment? The timing is not random. It is a profound clue etched into the life story of the cosmos. To understand it, we must consider the changing balance of power within the universe. For billions of years after the Big Bang, the cosmos was dominated by the dense, energetic soup of radiation and matter. Gravity, fueled by all this concentrated stuff, held a firm grip, putting the brakes on expansion. The universe was still growing, but at a steadily decreasing rate. As space continued to stretch, however, the density of matter and radiation diluted, their gravitational influence weakening with every passing eon. Dark energy, if it behaves like a cosmological constant, is different. Its energy density does not thin out as space expands, it remains stubbornly constant. Imagine two armies in a cosmic tug of war. On one side, the force of gravity, whose soldiers are becoming more spread out and less effective over time. On the other side, dark energy, whose strength per unit of space never wavers. About 5 billion years ago, the universe had expanded enough that the diluted grip of matter finally fell below the unchanging push of dark energy. That was the moment the balance tipped and acceleration began. This simple density argument is compelling, but it assumes dark energy is truly constant. What if its nature is more dynamic? Another fascinating possibility is a phase transition in the dark energy field itself. Think of water cooling, its molecules moving freely until, at a specific temperature, they suddenly lock into the crystalline structure of ice. Could the dark energy field have undergone a similar shift? Perhaps for most of cosmic history it existed in a high-energy state, dormant or weakly interacting. Then, as the universe cooled and expanded to a critical point, the field settled into a lower energy configuration, one that actively exerts the repulsive pressure we now measure. This would mean acceleration did not simply win by default as matter diluted, it actively switched on when the universe reached the right conditions. The difference between these two explanations is everything. One paints dark energy as a passive, eternal background feature finally revealed as the universe thinned out. The other suggests it is an active component that changed its state, triggering a new cosmic era. How can we tell which is true? The key lies in ultra-precise measurements of that transition epoch. By studying galaxies and supernova from around 5 billion years ago with incredible accuracy, astronomers hope to see if the onset of acceleration was sharp and sudden, like a switch flipping, or a smooth and gradual takeover as matter faded. That subtle detail in the data could reveal whether we live in a universe where dark energy has always been there, quietly waiting its turn, or one that underwent a fundamental change, entering a new and accelerating phase of its existence billions of years after the lights first came on. The timing of the cosmic acceleration hints at a universe fine-tuned for our existence, but what if our entire cosmos is just one possibility among an infinite number? This leads us to the 16th profound question: are there other universes with different expansion laws? The idea is not pure science fiction. It emerges naturally from our leading theory of the very beginning, cosmic inflation. In the scenario of eternal inflation, once the process starts, it may never truly stop everywhere. Instead, the inflating space becomes a frothing, bubbling sea where pockets of inflation randomly end. Each of these pockets, each bubble where inflation ceases, becomes its own separate universe with its own Big Bang and its own subsequent evolution. In this vast multiverse ensemble, the fundamental constants of physics, the strength of forces, the masses of particles, and crucially, the amount of dark energy or the nature of expansion itself, could be randomly set to different values in each bubble. Our universe, then, is just one bubble among a potentially infinite number, one where the cosmological constant happened to have the specific, tiny value we measure. In other bubbles, dark energy might be vastly stronger, causing a universe to inflate apart so rapidly that matter never has a chance to clump into galaxies or stars. In others, it might be zero or even negative, leading to a universe that collapses back on itself almost immediately after birth. This is where a controversial but fascinating idea enters: the anthropic principle. In its simplest form, it states that we can only observe a universe that is compatible with our existence as observers. We find ourselves in a bubble with a cosmological constant small enough to allow billions of years of gentle expansion for galaxies to form, stars to ignite, and planets to coalesce, yet large enough to eventually drive the acceleration we see. If we were in a bubble where dark energy was 1,000 times stronger, space would have accelerated into emptiness before the first star could ever shine, and there would be no one to wonder about it. The multiverse idea, coupled with the anthropic principle, offers a radical explanation for the puzzlingly small value of the cosmological constant. Instead of a single universe mysteriously fine-tuned for life, we have a near-infinite lottery of universes with all possible values. We simply live in one of the rare habitable winners. This perspective transforms the question from why our expansion laws are what they are, to why we find ourselves within this particular set of laws. It suggests our cosmic home may not be special or centrally planned, but simply a survivable neighborhood in a vast and wildly varied cosmic metropolis, most of whose districts are forever dark and lifeless. The multiverse offers a dizzying escape from fine-tuning, but it leaves a far more stubborn problem untouched, one rooted in the very fabric of empty space. Quantum theory paints a picture of the vacuum that is anything but empty. At the tiniest scales, space seethes with a turbulent energy, a frothing sea of virtual particles. These are not ordinary particles, but fleeting pairs of matter and antimatter that borrow energy from the vacuum, wink into existence for an unimaginably brief instant, and then annihilate each other, paying the energy back. This ceaseless, chaotic activity is not just theoretical. It has real, measurable effects in the lab, like the Casimir effect, where two metal plates placed extremely close together feel a slight push from the quantum activity in the gap between them. According to quantum field theory, the combined energy of all these frantic, short-lived fluctuations throughout all of space should contribute to the vacuum's energy density. This quantum vacuum energy is in fact the most natural candidate for Einstein's cosmological constant, for dark energy itself. It is the energy of nothing, and it should be pushing the universe apart. Here we arrive at perhaps the most embarrassing and profound failure in all of theoretical physics. When scientists perform the straightforward calculation to estimate the strength of this quantum vacuum energy, the result is not just a little off, it is catastrophically, incomprehensibly wrong. The predicted value is larger than the observed value of dark energy by a factor of 1 followed by 120 zeros. To put that in perspective, it is like predicting the weight of the entire observable universe, but the actual measurement comes back as the weight of a single grain of sand. This staggering mismatch is known as the cosmological constant problem, and it represents a yawning abyss between our two most successful theories, quantum mechanics and general relativity. One theory says the vacuum should be bursting with an energy that would have ripped the cosmos apart in a fraction of a second. The other, through observation, tells us the vacuum's energy is incredibly faint, just strong enough to drive the gentle acceleration we see. This is not a minor puzzle to be solved with a tweak. It is a screaming contradiction at the heart of reality. Some physicists hope a theory of quantum gravity will one day show how these wild quantum fluctuations somehow cancel each other out with near-perfect precision, leaving only the tiny residue we call dark energy. Others wonder if our very concept of vacuum energy is flawed. Could it be that the quantum jitter of the microscopic world simply does not gravitate in the way we assume? Or does the answer lie in the strange possibility that our universe is not unique, that we live in a multiverse where almost all possibilities have a vacuum energy too large for life, and we just happen to find ourselves in an astronomically rare bubble where the numbers, by sheer accident, almost cancel out? The cosmological constant problem is a humbling reminder that for all our cosmic mapping, we still do not understand the true nature of nothingness. That staggering failure to explain nothingness drives us to seek more tangible proof from the dawn of time. While the cosmic microwave background is a baby picture of the universe, it may hold a hidden image from an even earlier moment. Can we observe the kick from inflation directly? The theory says that in that first trillionth of a second, the fabric of space-time itself was violently stretched, creating ripples known as primordial gravitational waves. Unlike the gravitational waves we detect from colliding black holes today, these would be imprinted on the entire cosmos, a fossilized tremor from creation's first instant. Finding them would be the ultimate smoking gun for inflation, a direct observation of the universe's explosive birth cry. But how do you catch a whisper from the beginning of everything? The hunt focuses on a specific, elusive signature in the ancient light of the cosmic microwave background. Light can be polarized, meaning its electric field vibrates in a preferred direction. The hot and cold spots of the early universe created one type of polarization pattern, like radial lines or concentric circles, which we have already mapped. But the violent stretching of inflation should have generated something else, a distinctive swirling pattern in the polarization known as B modes. Think of the CMB as the surface of a pond. The regular hot and cold spots are like raindrops creating simple, expanding rings. Primordial gravitational waves would be like someone stirring the pond with a giant, cosmic spoon, leaving a characteristic curl or vortex in the patterns. Detecting that faint swirl is the goal. It tells us not just that inflation happened, but how powerful it was. The strength of the B-mode signal reveals the energy scale of that primordial expansion, telling us whether inflation was a gentle roll or a shattering quake in the fields that govern reality. The pursuit of this signal is a story of extreme science. Teams have built telescopes in some of the most remote, dry, and cold places on Earth, like the South Pole and the high Chilean desert, to peer into the cleanest possible sky. They must filter out not just clouds, but the faint polarized glow from dust in our own galaxy, which can mimic the signal they seek. Acclaimed detection in 2014 by the BICEP 2 telescope turned out to be largely from this galactic dust, a sobering lesson in cosmic foregrounds. The search continues with ever more sensitive instruments, each one a time machine trying to decode a spiral pattern written in the first light, a direct message from the moment our universe was born. The search for primordial gravitational waves pushes us to the limits of observation, but what if the acceleration they helped seed is not even real? This brings us to a radical and deeply unsettling question. Is the expansion an illusion or a gravitational effect? A small but dedicated group of cosmologists is pursuing a heretical idea that dark energy does not exist at all. Instead, they argue the observed acceleration could be a grand cosmic mirage, a trick of perspective caused by the universe's own lumpiness. We have long assumed that on the largest scales, the cosmos is smooth and uniform, an assumption baked into every calculation of the expansion rate, but the real universe is anything but smooth. It is a tapestry of extreme contrasts, with dense clusters of galaxies containing trillions of stars and vast, nearly empty voids spanning hundreds of millions of light years. General relativity tells us that gravity behaves differently in these regions. Inside a dense cluster, space-time is highly curved and the local expansion is strongly suppressed. Inside a giant void, however, where gravity's pull is much weaker, space can expand faster. We do not live at an average point in the universe. We live inside a galaxy, which is inside a cluster, which is part of the cosmic web. What if our local measurements are not giving us a true global average, but a distorted view? This idea is formalized in theories of backreaction. The concept is that the complex hierarchical clumping of matter over billions of years does not just happen within space-time, it actively changes the average behavior of space-time itself. The gravitational backreaction of all these structures could, in principle, create an overall effect that looks like an accelerating expansion from our particular vantage point without any mysterious dark energy. Think of it like trying to measure the average temperature of Earth from a single location. If you are standing in a desert, your measurement will be skewed hot. If you are at the North Pole, it will be skewed cold. To get the true global average, you need a method that accounts for all the extremes. Proponents of backreaction argue that our standard cosmology has made a similar error, mistaking our local, structured environment for the smooth, averaged universe of our equations. They are building sophisticated models that treat the cosmos not as a simple, expanding fluid, but as a Swiss cheese of dense regions and empty bubbles, calculating how light travels through this complex terrain. The goal is to see if the observed dimming of distant supernova, the very evidence for acceleration, can be reproduced purely from this gravitational lensing and differential expansion. So far, the consensus is that backreaction alone cannot fully explain the data. The observed acceleration is too clean, too consistent across different directions and different measurement techniques, from supernova to the cosmic microwave background. Creating such a uniform illusion from a chaotic distribution of matter is a monumental challenge for these models, yet they represent a vital and necessary line of inquiry. They force us to question our most fundamental simplifying assumption, the cosmological principle itself. They remind us that the universe is not a textbook diagram. It is a dynamic, structured, and messy place, and our interpretation of its expansion must ultimately account for every last detail of its magnificent complexity. These vast cosmic deserts are not just empty space, they are active players in the expansion drama. If dark energy is the engine of acceleration, then cosmic voids are its open throttle. These are the regions where the universe is emptiest, where galaxies are few and far between, spanning hundreds of millions of light years. They are not truly empty, of course, but their density of matter is perhaps only 1/10 the cosmic average. And because there is so little matter inside them, the gravitational pull holding them together is incredibly weak. This allows the repulsive push of dark energy to work almost unopposed. Within these titanic bubbles of near nothingness, space itself is stretching faster than the universe's average rate. They are the fastest expanding places in the cosmos. Now consider our own position. We live not in a void, but within the rich structure of the Laniakea supercluster, a web of galaxies. But what if our entire local supercluster resides inside a much larger, underdense region, a so-called Hubble bubble? This is not a wild idea. Some analyses of galaxy surveys suggest our cosmic neighborhood might be part of an underdensity stretching over 1 billion light-years. If that is true, it would profoundly bias our local measurements of the Hubble constant. Our telescopes would be measuring an expansion rate that is boosted by the void's rapid internal growth, a rate that is not representative of the true, global average of the universe. It would be like trying to determine the average speed of all cars on a highway by only measuring the ones in the fast lane. Our local, faster measurement would naturally clash with the global average derived from the early universe's smooth cosmic microwave background, potentially explaining the Hubble tension without any new physics. The voids are not just testing grounds for expansion, they are also cosmic construction sites. Their rapid growth squeezes the matter around them, helping to sculpt the filaments and walls of the cosmic web. They act as immense gravitational shadows, their emptiness pulling galaxies toward their dense edges. This intricate dance between the emptiest places and the richest structures is a direct consequence of the competition between gravity and dark energy, written across the largest possible canvas. To understand the true expansion of everything, we must first learn to read the silent, accelerating growth of nothing. The silent growth of cosmic voids underscores a simple truth: we need a clearer map. Our current view of the cosmic expansion is like trying to understand a continent by looking through a keyhole. The next decade will change that as a new generation of cosmic observatories swings open the doors to a panoramic, three-dimensional view of the universe's history. These are not just bigger telescopes, they are time machines and cartographers designed to dissect the dark energy puzzle with surgical precision. Leading the charge from space is the European Space Agency's Euclid telescope. Launched in 2023, Euclid is embarking on a 6-year mission to survey over a third of the extragalactic sky. Its primary weapons are extreme sharpness and stability. Euclid will image billions of galaxies, measuring their shapes with incredible accuracy. Why shapes? Because of a phenomenon called weak gravitational lensing. As light from distant galaxies travels toward us, it passes through the vast webs of dark matter that structure the cosmos. The gravity of these invisible filaments subtly bends the light, distorting the shapes of the galaxies in a specific statistical way. By mapping the subtle warping of billions of galaxies, Euclid will create the most detailed chart of dark matter's distribution ever made. This map is a direct record of how structure has grown over cosmic time. Since dark energy suppresses this growth by pushing matter apart, any deviation from the predicted growth pattern will reveal the strength and evolution of the repulsive force. Euclid will also measure the redshifts of tens of millions of galaxies, allowing it to construct a three-dimensional map and measure the Baryon acoustic oscillations, those frozen sound waves from the early universe across an unprecedented volume. Joining Euclid in the mid-2020s will be NASA's Nancy Grace Roman Space Telescope. Roman has a different, complementary superpower, a field of view 100 times larger than the Hubble Space Telescopes. This enormous cosmic eye will conduct sweeping surveys at an astonishing pace. One of its flagship projects is to discover and measure thousands of the most distant Type 1 supernova. While current surveys have found hundreds, Roman will find thousands, pushing deeper into the universe's past to precisely chart the transition from deceleration to acceleration. It will see the moment dark energy took over with a clarity we have never had. Rubin will also perform its own gigantic weak lensing survey, cross-checking Euclid's results and providing an independent, powerful measurement of how dark matter clumping has been slowed by dark energy. On the ground, in the clear skies of Chile, the Vera Sea, Rubin Observatory is preparing for a different kind of revolution. Its 8.4-meter mirror and massive 3.2 gigapixel camera will scan the entire southern sky every few nights for a decade, creating an unprecedented motion picture of the cosmos. This legacy survey of space and time will detect tens of billions of galaxies and, crucially, will spot millions of transient events, including supernova, in real time. Rubin's relentless watch will catch supernova at their very moment of peak brightness, allowing for exquisitely precise distance measurements. It will also map the cosmic web in staggering detail, tracking how the distribution of galaxies changes over the most recent several billion years. Together, these observatories form a triangulation strategy. Euclid provides ultra-sharp, deep maps of dark matter. Rubin delivers a vast, deep census of supernova and its own wide field maps. Rubin offers a continuous, all-sky movie of change and discovery. They will measure the expansion history, the growth of structure, and the geometry of the universe with a combined precision that is an order of magnitude beyond anything we have today. They are not looking for one single clue, but for a consistent story told by multiple, independent lines of evidence. If dark energy is dynamic, these tools will see its fingerprint in the data. If our local measurements are biased by a cosmic void, these global surveys will reveal it. If there is new physics modifying gravity on large scales, the inconsistencies will become undeniable. We are on the verge of moving from an era of mystery into an era of measurement, where the whispers from the dark universe will finally become a clear, unmistakable voice. But what if the map itself is flawed? Every measurement of the universe's expansion, from distant supernova to ancient sound waves, relies on a hidden, unshakable assumption that the clock ticks at the same rate everywhere and everyone. We assume a second here and now is identical to a second 5 billion years ago in a faraway galaxy. But what if that is wrong? Could time itself be changing? This is not science fiction, but a radical frontier in cosmology that turns the mystery of dark energy on its head. Imagine the universe is not accelerating at all. Instead, what if time flowed more slowly in the distant past relative to us today? From our perspective, watching the ancient light from a supernova billions of years away, its explosion would appear to be stretched out, its light dimmer and redder over a longer duration. This stretched signal could perfectly mimic the signature of an accelerating expansion, tricking us into believing galaxies are flying apart faster and faster, when in reality, the very pace of time has shifted. This idea connects to speculative theories where fundamental constants, like the speed of light or the strength of gravity, are not constant at all but evolve over cosmic epochs. In some of these models, as the universe ages and cools, the underlying fabric of reality undergoes subtle changes that affect how clocks run and how light travels. If the speed of light was higher in the early universe, for instance, it would alter how we interpret cosmic distances and redshifts, potentially erasing the need for dark energy. While these theories are highly controversial and face significant hurdles, their power lies in the profound question they force us to ask. Our entire cosmic model is built on the principle of uniformity, that the laws of physics are the same everywhere and at all times. This principle lets us use the light from the early universe as a reliable textbook. But if time or other constants can vary, that textbook is written in a language that changes from chapter to chapter. We would have to learn to read it all over again. The search for dark energy, then, becomes something even deeper, a test of whether the most fundamental rules of reality are truly eternal or if they, too, have a history written in the slow, silent ticking of the cosmic clock. The vacuum catastrophe is not just a problem, it is a screaming contradiction in the heart of physics. We have two pillars of modern science, quantum field theory and general relativity, and they disagree about the energy of empty space by a factor of 1 with 120 zeros after it. This is the single worst prediction in the history of science. To grasp the scale, imagine predicting the weight of every star in every galaxy across the entire observable universe. Now imagine the actual measurement comes back as the weight of a single bacterium. That is the level of our failure. The quantum vacuum, that seething sea of virtual particles, should be exploding with an energy density that would have ripped the cosmos apart in a fraction of a second after the Big Bang. Yet what we observe as dark energy is a faint, gentle pressure, a ghost of that predicted fury. So what went wrong? Either our understanding of the quantum vacuum is fundamentally flawed, or something is cancelling out almost all of that titanic energy with unimaginable precision. One proposed fix is a concept called supersymmetry. This elegant theory posits that for every known particle, there exists a superpartner particle. The crucial point is that the quantum contributions of these particle pairs could have opposite signs, causing their vacuum energies to partially cancel each other out. It is a beautiful idea that solves other problems in particle physics, but even if supersymmetry is real, it only reduces the discrepancy. It might bring the prediction down by a factor of 1 followed by 60 zeros, which is progress, but still leaves a gap wider than the cosmos itself between prediction and observation. This leads to a more radical and for some unsettling answer, the landscape multiverse. In this view, the vacuum energy is not a single number set by fundamental law, but a variable that can take on almost any value across a near infinite number of bubble universes. In the vast majority of these bubbles, the vacuum energy is enormous, leading to instant cosmic collapse or runaway expansion, universes stillborn or empty. Only in an astronomically rare subset like our own does the random number land in the tiny, habitable range where galaxies can form. We are not in a fine-tuned universe, we are in a survivable one. The anthropic principle returns not as an explanation, but as a selection effect. We could never find ourselves in a universe where the vacuum energy was 1 trillion times stronger because no one would be there to look. The final possibility is the most mysterious of all, that some deep, undiscovered principle of quantum gravity forces a near-perfect cancellation. Perhaps the wild quantum fluctuations of all fields somehow add up to zero, and the tiny dark energy we see is a leftover residue from some other process or a correction we do not yet comprehend. This would mean the vacuum catastrophe is not a sign of failure, but a signpost pointing toward a deeper theory that marries the quantum world with gravity. Each path forward reshapes our reality. One suggests our universe is one lucky ticket in a cosmic lottery of unfathomable size. Another hints at a hidden symmetry so profound it tames the infinite. The vacuum catastrophe is more than a number. It is a direct challenge, a glaring signal that our map of reality is missing its most important continent, the true nature of nothing itself. That faint afterglow of creation, the cosmic microwave background, is supposed to be our cleanest, most uniform map of the infant universe. But what if this baby picture has strange, unexplained blemishes? The 24th Great Mystery asks if there are anomalies in this ancient light that could rewrite the story of our beginnings. For decades, the cosmic microwave background has been the cornerstone of our standard model, its near-perfect uniformity a triumph for inflation. Yet, as our satellites have mapped it with ever greater precision, a few stubborn, curious features have emerged, features that do not fit the expected pattern of random noise. They are whispers of something odd, perhaps a flaw in the lens or a sign of something beyond our current physics. The most famous of these is a peculiar alignment nicknamed, somewhat dramatically, the axis of evil. According to the standard model, the hot and cold spots in the cosmic microwave background should be distributed randomly, like a static pattern on an old television with no preferred direction. But several analyzers have suggested a strange correlation, an unexpected alignment of the largest temperature fluctuations along a particular axis in the sky. It is as if the universe has a subtle, preferred direction, a cosmic tilt that violates the foundational cosmological principle which states the universe should look the same in all directions. While the statistical significance of this alignment is hotly debated, its persistence in the data is puzzling. Could it be an artifact of our own motion through the cosmos, or contamination from our galaxy's foreground light? Or could it be a fossil from a time before inflation, a scar from a pre-existing structure that the inflationary burst failed to completely erase? Another deep chill in the data is the infamous cold spot. This is a region in the southern sky, spanning billions of light years, that is significantly colder than the surrounding average. It is too large and too cold to be easily explained as a mere statistical fluke. One compelling explanation is that it could be the imprint of a cosmic supervoid, an immense, nearly empty region of space between us and the surface of last scattering. If such a void exists, the light traveling through it would lose energy, stretched by the void's faster than average expansion, creating a cold patch in the map. Finding this proposed void has proven difficult, however, leaving the cold spot's origin an open question. Some have even speculated it could be evidence of a collision with another universe bubble in the multiverse, a cosmic bruise from a long ago encounter. Then there is the large-scale power asymmetry. The fluctuations in the cosmic microwave background appear slightly stronger or more powerful in one hemisphere of the sky compared to the other. Again, this challenges the assumption of statistical isotropy, the idea that the universe has no special left or right. These anomalies individually might be written off as statistical quirks or unaccounted for foregrounds. But together, they form a nagging pattern of unease. They suggest the possibility that our universe's initial conditions were not perfectly uniform and random as inflation predicts. Perhaps inflation did not last long enough to erase all traces of what came before. Maybe the topology of space is more complex than we think, not a simple infinite flat sheet, but a twisted or connected shape that leaves an imprint on the largest scales we can observe. If any of these anomalies are confirmed as real cosmological signals, the implications are profound. They would mean the seeds for everything, for all the galaxies and the vast cosmic web, were planted with a slight bias, a hidden directionality written into the fabric of reality at the moment of its birth. This would not just be a tweak to our models, it would be a fundamental challenge to the inflationary paradigm and a direct window into the ultimate initial conditions that set the entire cosmic expansion in motion. The universe's first light may hold a secret message, and we are only just beginning to decipher its strange, uneven handwriting. Those faint anomalies in the cosmic microwave background are not just curiosities, they are cracks in the foundation. Every single one of our questions, from the nature of dark energy to the fate of the cosmos, rests on an unshaken pillar, Einstein's theory of general relativity. It is the rulebook for gravity, describing how mass and energy curve the fabric of space-time. It predicted black holes, gravitational lensing, and the expansion of the universe itself. But what if, on the largest cosmic scales, this rulebook is missing a page? The final and perhaps most fundamental question is this: is our understanding of gravity wrong on cosmic scales? The accelerating expansion forces us to confront this possibility. General relativity, as stunningly successful as it is, contains no built-in mechanism for cosmic acceleration. To explain what we see, we had to invent dark energy, a mysterious component comprising most of the universe. For many scientists, this is a perfectly reasonable path, discovering new forms of matter and energy that our telescopes cannot see directly. But for others, it is a warning sign. Inventing an invisible, undetectable substance to fix your equations is reminiscent of the flawed concept of the luminiferous ether from centuries past. Perhaps the problem is not with the contents of the universe, but with the laws that govern it. This has led to a bold and controversial alternative, modifying gravity itself. The most famous of these ideas is modified Newtonian dynamics, or MUND, proposed in the 1980s to explain galaxy rotation curves without dark matter. MUND suggests that Newton's law of gravity, and by extension Einstein's, changes when gravitational acceleration becomes extremely weak, such as in the outer reaches of galaxies. In these regimes, gravity becomes slightly stronger than predicted, which could explain why stars orbit galaxies so quickly without needing invisible dark matter halos. MUND has had notable successes at galactic scales, but it faces immense challenges on the scale of the entire cosmos. It struggles to explain the precise patterns we see in the cosmic microwave background and the detailed clustering of galaxy clusters, phenomena that the dark matter model handles with remarkable accuracy. More importantly, the original MUND was not a relativistic theory. It could not be plugged into the equations of the expanding universe. To address this, physicists developed relativistic extensions like tensor vector scalar gravity, or TVS. These theories attempt to build a full, cosmic-scale alternative to general relativity that incorporates MUND-like behavior. Yet, even these more sophisticated frameworks have a hard time naturally producing the accelerated expansion we observe. They often still require some additional element, a cosmological constant or a new field, looking suspiciously like dark energy in disguise. This has spurred an even broader search for modifications to gravity that could explain everything, the phenomena attributed to both dark matter and dark energy with a single revised law. These are theories like F of R gravity, where the strength of gravity depends on the overall curvature of space-time, or scalar tensor theories, which introduce an additional cosmic field that interacts with gravity. In these models, the accelerated expansion is not driven by a mysterious substance, but is a geometric effect, a consequence of gravity itself weakening or behaving differently over vast distances as the universe expands and becomes emptier. The universe would accelerate because gravity's grip fades faster than general relativity predicts on cosmic scales. Testing these ideas is a monumental task. It requires looking for subtle deviations from Einstein's predictions in multiple, independent arenas. Does the bending of light around massive galaxy clusters, gravitational lensing, follow Einstein's rules exactly, or is there a slight discrepancy that a modified theory could explain? Do the orbits of stars within galaxies and the motions of galaxies within clusters all tell the same, consistent story under general relativity, or do they hint at a scale-dependent law? The most stringent tests come from combining all our cosmic probes, the cosmic microwave background, the large-scale structure of galaxies, the distances to supernova, and even gravitational waves. The goal is to see if a single, modified theory of gravity can fit this entire suite of data as well as, or better than, the standard model of dark matter plus a cosmological constant. So far, the standard model, with all its mysterious components, remains the most parsimonious fit to the universe we observe, but the hunt for a gravitational alternative is far from over. It represents the ultimate scientific humility, the willingness to question our most celebrated theory when faced with the unknown. Whether the answer is a new component of the universe or a new law governing it, we are witnessing a pivotal moment, a deep and necessary stress test of our understanding of reality, conducted across the boundless laboratory of the cosmos itself. From the quantum foam of space-time to the silent growth of cosmic voids, we have journeyed through 25 of the most profound mysteries in existence. Each one is a thread in a single, magnificent tapestry, and at its center lies the accelerating expansion of the universe, This is not a side puzzle. It is the central enigma of our age, the question that defines modern cosmology. Whether it is driven by a dynamic dark energy, a flaw in gravity, or an echo from hidden dimensions, the answer will reshape our understanding of reality itself. Solving these riddles may require a revolution in physics as profound as those brought by Einstein's relativity and the birth of quantum mechanics. We stand at a thrilling precipice, armed with telescopes that are time machines and surveys that map the history of everything. The universe itself is posing these questions, whispering clues in the light of ancient supernova and the subtle patterns of the first light. The next great discovery, the one that finally illuminates the dark cosmos, could be just around the corner. Which of these 25 mysteries keeps you wondering? Share your thoughts in the comments below and subscribe to join us for more deep dives into the universe's biggest secrets.